talk of the Midwest PL Summit will be Ryan Scott talking about constructing very large proofs very easily with verified classes library.
Thank you. My name is Ryan, not that Ryan, the other Ryan. And today I'm going to be talking about type classes. So I'm going to pick one of my favorite type classes here, ORD, which if you have an instance of ORD, it'll let you check if one thing is less than or equal to something else using this little operator here. So fun fact about ORD is that it's more than just this method. It also comes with this expectation that when you write ORD instances, that the implementation of less than or equals should obey certain laws, such as anti-symmetry, reflexivity, transitivity, and so on and so forth. And what better way to communicate laws to programmers than with comments? So here's one example of a law written as a comment, which transitivity states that if you have x less than or equal to y and y less than or equal to z, then you can apply transitivity and stick them together, get x less than or equal to z. So the downside of writing laws in comments is that they're also enforced with comments, which is to say they're not enforced at all. If you write an ORD instance, it is very easy to either goof up or just intentionally write something that does not obey the laws, and that's not great. We like to be able to have these laws in mind when we're reasoning about this code. So we can do a little better than this. Instead of writing with comments, we can write a subclass of ORD for verified ORD instances, or VORD for short, and we can write the statement of the transitivity law as a type signature. And this way, if you want to have some assurance that this code actually obeys this law, then when you write an instance of VORD, you actually have to write a proof that this thing is in fact transitive. So that's a little bit better, but I still claim it's not ideal. And the reason it's not ideal is because when you write proofs for these things, they can blow up in size really quickly. Even for a relatively small data type that only has like 3 constructors, the proof of transitivity is really large. So large that I have to shrink down the font size quite a bit to get to fit on a single slide, and you probably can't read that in the back, and that's intentional. Don't read this. This is terrible anyway. We shouldn't aspire to do this in the first place. What we should aspire to do is to have something that's closer to this really slick one-liner, or almost one-liner, where we use this generic default implementation of transitivity. And this should not only work for the definition of T that I've shown here, but really should be able to work for any data type that we might throw at it. So if we have an arbitrary number of constructors or fields or what have you, we should be able to use the same almost one-liner and get a verified implementation of transitivity for our ORD instance. So that's what we want to aspire to do, and well, that's what we did. So how do we do this? Well, as we all know, the first step when writing a new library is publish a paper about it. So we did that part. It's published in the 2019 Haskell Symposium. So if you're curious, check it out. Unfortunately, I don't have time to really talk about it, so I'm just going to have a slide that shows the paper and nothing else. The one thing I want to point out about this paper title is the use of the word generic in it. And this is because we apply a lot of nifty tricks from data type generic programming to make it all possible. So there's your teaser for the paper. So the next step when writing the library is we have to pick a language to write it in. I mentioned earlier that we needed dependent types in order to write the type signature for LAQ transitive. So what's the best dependently typed language? Of course, it's Haskell. And we chose Haskell because we're bold, adventurous programmers. But if you want to stick to a more conventional dependently typed language, we also have ported some of the library over to Coq to show that it is in fact possible. So pick your poison. So the last thing we need to do when writing this library is pick a convincing use case for it. We decided to look close to home, and we looked at the base library in Haskell. And the reason we chose base is because this is a pretty notable collection of a lot of type classes with associated type class laws that we could pick from. To illustrate this sort of thing, there's a famous diagram in the Haskell community called the type classopedia that shows the subclass relationship between a lot of the more notable classes in base. And from this type classopedia, we were able to come up with generic default implementations for all the things that we shaded in yellow. So that's already a pretty good chunk. Obviously, there are more that we could fill out, but we'll leave that to future work. So great. This means that if you want an implementation of the laws for the classes in this diagram that are shaded in yellow. All you have to do is download our library and plug in the almost one-liner that is associated with that class. Pretty cool, huh? So you're probably wondering what the catch is. The catch is there's still some remaining work to be done in terms of the compile time efficiency of this thing. I think this chart here best illustrates the issue. The x-axis shows all the classes that verified classes library supports, and the y-axis shows the time it takes to compile that part of verified classes alone, like not the instances, but just the modules themselves in verified classes. So for some type classes, it's not so bad, maybe on the order of a couple seconds or so, but in certain cases, it degenerates and really blows up in compilation time, like on the order of like 15 or 20 or more seconds. And we have some ideas as to why this happens. The short version is that when you compile this code, GAC, the Haskell compiler we're using, generates a lot of coercions, which the optimizer has a really hard time dealing with. And we have some ideas how we could possibly tweak GHC to get it to emit fewer coercions and not punish the simplifier as much, but that is ongoing work. So I'll wrap things up by mentioning again that verified classes is available online at GitLab at the moment. I'm hoping to add some more polish in the coming weeks and eventually make a public release of this. But if you're writing out type class laws and you're tired of all the repetitive boilerplate code that comes with it, you might consider verified classes as a way to get rid of that boilerplate, and it offers an interesting point in the design space alongside other techniques such as tactics or proof search or things of this nature. So that's all I have to say on the topic. Thank you.
We have plenty of time for questions for Ryan.
Could you give a little bit more of detail how this generic default implementation, you showed for the ORD, yeah, default like transitive. Can you give me an idea how you would write one of those?
Yeah, I definitely glossed over a lot of the finer details for the sake of time, but the gist of it is that we use this module in the base library called GEC generics, which is kind of a minimalist data type generic programming library. So what you do is for a data type you want to have a default implementation of laws for, you would come up with an isomorphism for the original data type to some generic representation type that the GEC generics knows about, and then you can write proofs over the representation type, and then once you do this, the proofs, the original data type, come for free, where free means already paid for. So you end up writing a lot less code than you would if you write the proofs, the original data type, since the representation type typically is much more compact, and there's a lot less code you have to write to come up with the proofs for that.
Any other questions?
How complicated of type class laws can you process with this? It looked like monad was in the list of things you could cover, so you can do laws that deal with arbitrary functions with this.
Yeah, how complicated of laws can we prove? As you said, we have evidence that we can handle pretty, well, I don't know if complicated is the right word. We can certainly handle higher order things like the laws for functor or monad. Writing that in Haskell is a bit of an interesting story, but I'll save that for a future discussion. I'm trying to think if there are some like outright limitations on things that we can't do. None come to mind. I think the biggest limitation is finding a way to express the default in terms of the GEC generics representation types themselves, because that is basically the trick that allows this whole thing to be possible. So there are some representation types for which writing default instances is not always feasible. Like the one that comes to mind is the semi-group laws. If you try to write those for some types, then the choice of implementation is not always clear. So we deliberately omit handling sum types for the semigroup laws, for instance. There are certainly like some types in the wild that could have semigroup instances, but coming up with a suitable default implementation that covers all sum types seemed to be a bit of a stretch, so we decided not to do that.
Okay. Well, let's thank Ryan again. So that concludes the session.